Singular value decomposition offers geometric intuitions to describe the transformation matrix A. In the following, we will discuss singular value decomposition as sequential linear transformations performed on bases. We will then apply transformation matrices of the singular value decomposition to a set of vectors in R2, which allows us to visualize the effect of each transformation more clearly. The singular value decomposition of a matrix can be interpreted as a decomposition of a corresponding linear mapping phi from Rn to Rm into three operations. Assume we're given a linear transformation matrix of a linear mapping phi from Rn to Rm with respect to the standard bases B of Rn and C of Rm. Moreover, assume a second basis B tilde in Rm, Rn, and C tilde in Rm. Then the matrix V performs a basis change in Rn from B tilde to the standard basis B. The change from B tilde to B is performed by V transpose, which is equal to V inverse. We can see this if we start in the top left corner of the diagram, applying V transpose will now line up our vectors V1 and V2 with our standard basis E1 and E2. Having changed the coordinate system to B tilde, applying sigma now scales the new coordinates by the singular values sigma I and adds or deletes dimensions. That is, sigma is the transformation matrix of phi with respect to B tilde and C tilde, represented by the red and orange vectors being stretched and lying in the E1, E2 plane, which is now embedded in a third dimension in the bottom right of the figure. Finally, U performs a basis change in the codomain Rm from C tilde into the canonical basis of Rm, represented by a rotation of the red and orange vectors out of the E1, E2 plane. This is shown in the top right corner of the figure. The singular value decomposition expresses a change of basis in both the domain and codomain. What makes the singular value decomposition special is that these two different bases are simultaneously linked by the singular value matrix sigma. Consider a mapping of a square grid of vectors x in R2 that fit in a box of size 2 by 2 centered at the origin, the top left corner of the figure. Using a standard basis, we map these vectors using matrix A. And since A is equal to U sigma V transpose, we're going to start by taking our set of vectors and rotating them after applying V transpose. The rotated vectors are shown in the bottom left panel. Now we map these vectors using a singular value matrix sigma to the codomain R3. That's in the bottom right. Note that all the vectors lie in the x1, x2 plane. The third coordinate is always 0. The vectors in the x1, x2 plane have been stretched by the singular values. And then finally we map it to the fourth panel. In the next section, we'll discuss how to actually construct this singular value decomposition.